I'm gonna, even though we skipped 6.5, I want to very briefly go over 6.5. 6.5 says assessing normality. Okay, how do we actually take something and look and see if it's normal? Okay, so what we would normally do is that we would just go ahead and do a dot plot. If there, if there are few enough things. If you have like 1,000 points, you can't actually draw it, right? I mean, we're not going to sit there and do a dot plot for 1,000 points of data, right? But if they're like something manageable, 30, 20, then you just do the dot plot. And what are you looking for then when you're assessing normality? What would you look to see? Okay, well, so yeah. Well, you want to see if it's symmetric, right? See if it's roughly symmetric, right? And you're also looking for outliers and skewness, right? Outliers and skewness is really what you're looking for. And those are the two. If they don't have a huge skewed or there are no outliers, you're going to say, oh, looks roughly normal to me. You just move on, right? You're going to say it's just normal, okay? We assessed the normality and said, yes, it's normal. Okay? Now, if you go to your calculator, there is actually a thing called normality plot. There's a plot that actually you can use, and it plots the data. And if you go to page, we're on page 277. 276 and 277. If you look at 276 and 277, there are 2 or 3 plots there, okay? And you're looking, as you can see there, some of them are linear, correct? Some of them are not. You're looking for a linear plot. You want a plot that comes out linear. And then you would say, oh, well, that looks normal to me, okay? If they are not normal, which one would be not normal? There are 3 of them there. There's the one on 276, then on 277 there's one that's kind of linear, and then the one on the bottom is absolutely not linear, correct? So the one on the bottom you would say, no, this does not look like a normal distribution, okay? All right. So that's how you would do it. I'm just trying to let you guys know that there is a way to do it, okay? There is a way to put in your calculator and figure it out, okay? All right, so move on. Let's go on to actually 6.6 now, and we will do normal as approximation to binomial, okay? So we're doing normal as approximation to binomial. So what we're doing is we are taking a binomial distribution and saying that, whoa, it's normal, and we're just going to move on. So we're going to take a binomial. Anybody remember what the conditions that have to be met for something to be binary? Huh? Binary is one. What else? Bin. So it's independent. Number of trials are set. And then same numbers, same probability. Same probability.
Exactly.
Okay? So there are bins, right? These are the conditions. Remember we had the 4 conditions that have to be met. That's what we're looking at. So we have a probability. Okay, we have a probability. And then we have what? So so this is going to be NP. It's the expected value, right? If we do it so many times with this probability, this is going to be the mu, and then we have this of, and we've done this before, NPQ. Remember that? Does this kind of ring a bell? Yes. 1 or Q is 1 minus P here. 1 minus P. So this is all you really have to know. Okay? There has to be conditions that have to be met for you to use this, and those are on page 285. 285, okay. We are going to do a, there isn't something here, but I will tell you, normally, the three conditions are, it has to be a simple random sample. So it has to be a random sample. 2, you are never allowed to oversample. You cannot sample more than 10% of the entire population. And then there 3 is what we call the large counts. And this has to be greater than 5. Okay. In other words, this guy here has to be greater than 5. Okay. So if I drew a sample of 500, okay, and I found that 100 people were, or let's, I don't know, let's say 20 people ended up being left-handed. Okay, left-handed. Then the probability of being left-handed would be what? 20 out of the 500, correct? So your NP is going to be what? What was my N? 500, right? Right? 20. What's your NQ? What's NQ? NQ is basically N1 minus P, which would be 500 times 1 minus the probability. Everybody see that? 500 times 1 is 500. 500 times this is 20. So it's the remainder, right? Those that are not left-handed, right? Because you're either left-handed or right-handed. We're not doing the ambidextrous. We're not going to that. Okay, so either you are, because it's binary, right? You have to be either left-handed or right-handed, right? Okay, so it'll be 480. So again, so both of these have to be greater than 5. Okay, both have to be greater than 5. Okay. So let's say if we can get this to go. Okay, there's also something called the continuity correction. Okay, that's when we're on page 285. When using the normal approximation, adjust the discrete whole number x by using a continuity correction so that any individual value x is represented to the normal distribution by the interval of x minus 0.5 to x plus 0.5. You're probably thinking, what the heck is he talking about? I have no idea what this is. Okay? Don't be dismayed. We will talk about it. If you just read it like this, it makes no sense. But we'll do this in example 1. So we'll go on to example number 1, see what this actually means. Okay? Example number 1. In one of Mendel's famous hybridization experiments, he expected that among 580 offspring peas, 145 of them, or 25%, would be yellow. But he actually got 152 yellow peas. Assuming that Mendel's rate of 25% is correct, find the probability of getting 152 or more yellow peas by random chance. That is, given that n is equal to 580 and p is equal to 0.25, find large p. Okay? So, Mendel. Can anybody tell me, explain to me who Mendel was, what he did, what's going on, what did he do?
Was he like a monk or a priest?
He was a what?
Was he like a priest?
He was a...
Or a monk?
He was a monk, right? He was a monk. Okay, and he grew peas. He grew peas, right? And you learned this in what? In biology?
Yeah. Was he like the father of genetics?
He is the father of genetics. Right? He's the guy who talked about the recessive gene, right? Okay, all that stuff, all that good stuff.
He's not natural selection.
No, that's
That would be Darwin, right? Okay, so what do we have here? We have NP. What is my N? 580. My P was 0.25, right? So this is going to be equal to what? This is going to be equal to 580 times 0.25 times 1 minus 0.25, which is 0.75, right? And if I do this, the book tells me I get 10.42. 10.42. Okay, so the question was, I have this, which turns out to be 145. 145, and I want to know that it was greater than 152, correct? Okay. Am I allowed to have 152.13 P's?
No.
I am not, right? It's either 152 or 153, right? Or 151, 150. They are discrete. They're not continuous. Okay, a normal distribution is continuous, correct? And we are normalizing, we're going to say that this binomial distribution is a normal distribution. So we're going from a discrete distribution to a continuous distribution. So this is what we're going to say. So instead of saying what is greater than 152, I'm going to look to include that 152. I'm going to look to say 151.5 or greater. Does that make sense? Right? Because that is what we're going to say it's going to include the 152. Okay, so we're going to do this. And this is what the continuity correction was. Okay? In other words, since we're going from a discrete to a continuous one, if you read, let's read that one more time now, let's see if it makes sense. When using the normal approximation, you adjust the discrete whole number x by using a continuity correction, so that any individual value x is represented in the normal distribution by an interval between x minus 0.5 to x plus 0.25. When would you use the x plus 0.5 here? Can anybody tell me when you would use that?
Something like less than?
Correct. When it's on the other side, right? So if you are looking for 152 and lower, you would go 152 and a half. When you're looking for higher, to make sure that the 152 is included, you would go 151.5. Exactly that, right? So it turns out it wasn't that big of a deal, but when you read it, it's like, oof, I have no idea what this guy's talking about. Okay? All right, so now we did all the calculations. So what do I need to do? How am I going to do this? Norm CDF maybe? Right, I'm looking for this. So what would my lower level be? 151.5, high limit of 580. It's not going to be greater than 580. 580, right? I have only 580. And then my 145, 10.42, correct? And Evan is running the numbers. And so is Santos. Let's see if the two agree.
2 brain cells.
266.
Huh?
0.266.
0.2664. Santos, is he correct?
Mm-hmm.
Okay. So, let's see what happens if I actually did not do the correction. If I did not do the correction, I would do the what? Not this, but
152.
I would do 152, correct? So, put in 152 and tell me what you get. Shouldn't that be that big of a difference?
0.2508.
0.2508. Okay? So can you see the difference there? There's a bit of a difference, but not too much. It's 1.64%, I guess. Right? Okay. But there is somewhat of a difference, right? Okay. That's that. And so we actually talked about the continuity correction, and we will do example number 2 tomorrow. So we will call it a day today. Okay?